So first of all, let us start with these waveforms. These are the waveforms of the drain of the Mosfet in the primary side of high frequency transformer. This portion of waveforms is due to the DC equivalent of the maximum AC voltage of 25 volts AC coming from the line. The DC equivalent of this AC voltage is √2 times 265, which is about 380 volts. Above this, the voltage spikes due to the leakage inductance of the transformer primary also gets superimposed, which are denoted by VL here. Now let us assume that the output voltage of our flyback converter is 12 volt DC. The drop on the rectifier diode is 0.7 volt. Then one can say that the voltage of the secondary winding is 12.7 volts. When this secondary winding is conducting, then the voltage gets reflected to primary side of the transformer, which get amplified by a factor of turns ratio. This voltage is denoted by VR. The Mosfet also has to withstand this extra voltage stress. This is the formula of reflected voltage. Turns ratio is given by Np upon Ns. Hence the total voltage stress on the drain of the Mosfet will be a summation of maximum DC voltage due to line input plus the voltage spike due to leakage inductance of the transformer plus the reflected voltage. As a general rule of thumb, the voltage due to leakage inductance is taken as 30% of the maximum input DC voltage. Also, one needs to have at least 30% margin above the total voltage in the selection of the Mosfet. For our design, if we calculate the reflected voltage, the value of the primary turns Np is 88 and secondary turns is 11. Secondary winding voltage is 12.7, that is VO plus VD. So the reflected voltage will be about 102 volts. So for output voltage of 12.7 volt and diode drop of 0.7 volt, the secondary winding voltage and the reflected voltage is about 12.7 volts and 101.6 volts respectively, as it can be seen in the diagram. The 101.6 volts will be conducting through the primary winding and will be subjected to the drain of the Mosfet, which is internal to the tiny switch. We can also see that in the design results, the PI expert has also given these voltage ratings as 101.6 volts as the reflected voltage. Let us now calculate the total voltage stress on the Mosfet in the Matlab editor. For maximum input voltage of 265 volt AC, maximum input DC voltage will be 265 times √2. VL is 30% of maximum input DC voltage. Np and Ns is primary and secondary winding turns, which is 88 and 11 respectively. Output voltage VO is 12 volts and VD is the diode voltage drop, which is 0.7 volts. Now if we keep 30% margin, then the maximum voltage on the drain of the Mosfet comes out to be 766 volts. If we keep 20% margin, then it comes out to be 660 volt. But it is insufficient. From the PI expert design sheet, we can see that the maximum voltage that the internal Mosfet can withstand is 700 volts. So one needs to implement a snubber circuit to protect it from voltage stresses. So this much will be for today's video, guys. In the next video, we will be looking at the snubber circuit and its design. Thanks for watching. Drop a like if you found this video helpful. Leave a comment if you have any query regarding the topic. And don't forget to subscribe and share this video with others.